Um, First, let's have a look at salt hydrates. So we're talking now about on absorption in solids. Well, I've shown you this figure before. Here we have calcium chlorides, and here we have calcium chloride 6 hydrates with all the water molecules in crystal lattice. Then here we have the total energy released in kilojoule per mole versus number of water molecules in my material. And I just put some salt hydrates in here. And as you can see, it's fairly nicely a straight line. In addition, I plotted here the line representing the amount of energy required to vaporize the same amount of water. And as you can see, the evaporation energy is a bit less than reaction enthalpy, but not that much. This means that if I add water vapor to my salt, in the case of 8 molecules of water, this amount of energy would be released. If I would pour liquid water on my salt, then this amount of energy would be released. Because I will need this amount of energy to break the bonds between the water molecules in the liquids. So there is a clear reason why in these absorption storage systems you want to work with vapors instead of liquids, because if you work with vapor adhering to it, you get a much larger energy density than if you would pour a liquid over the solid. Well, are there many salt hydrates? Yes, there are. And you can see, well, over here I just plotted antions for different types of salts. So, for instance, if we look at magnesium chlorides, we can have 6, we typically under ambient conditions have 6 hydrates. Calcium chloride, we can get 6 hydrates. Strontium chloride, 6 hydrates. Barium iodide, 7 hydrates. Sodium sulfates, 10 hydrates, our famous Glauber salt. We'll still know from the PCM applications. Sodium selenide, 16 hydrates. Potassium selenide, 19 hydrates. However, these are not very convenient because selenide is a very unpleasant material to work with. So, but as you can see, many salts form hydrates. Now, if we have a fully dried material and we add water vapor to it, you will see that the first, over here, this is the first water molecule is attached more strongly than later water molecules. Over here, I plotted the reaction enthalpy for a large set of materials. For the first water, the blue one, and for the other waters, the average for the other waters, the purple one. And as you can see, the first one generally is substantially stronger attached. We can also see that if we want to dry a salt hydrate. Over here, I show you the thermogravimetric plot of magnesium chloride, 6 hydrates. In a thermogravimetric plot, we measure the mass of our sample as a function of temperature. What happens if we increase the temperature? At some point in time, vapor will be released, so our sample will lose weight because the vapor disappearing from the system. So you can see we start with the 6 hydrates, and then first we heat up 6 hydrates, and then we see that the 6 hydrates loses water vapor and goes to 4 hydrates. Then again, the 4 hydrate goes to 2 hydrates, then the 2 hydrate goes to monohydrates, and then we see a hydrolysis effect where HCl is produced. The reason why I show this curve is that you can really see that the water vapor comes off in a number of distinct steps, each having its own equilibrium temperature. To explain the concept of equilibrium further, it's convenient to first have a look at this that you already know, of the equilibrium pressure of water in a system. I've shown you this curve when talking about pressurized water and steam accumulators already before. Here we have the temperature, here we have the equilibrium rate in bars, and we can see that at 100 degrees our equilibrium pressure is exactly 1 bar. So this is for water vapor. Now I put here vapor pressure versus temperature, again for water and also for ammonia and water. Note that now I plotted this on a logarithmic scale. So the curve for water is exactly the same, but now plotted logarithmically. And as you can see, this is still at 1 bar, which it should be. You can also see that equilibrium pressure for methanol at this temperature is much higher. Water molecules have a strong binding, OH bonding in the water. For methanol, this effect is less, so we can see that we have a higher equilibrium pressure vapor. For ammonia, it's again less. You can see that at this temperature we would have very high ammonia pressures if we would have liquid vapor ammonia system. So, yeah, well, high ammonia pressures. Now, something similar I can do with salt hydrates. Over here, you see again the vapor pressure for water. And here you see the vapor pressure for sodium sulfite 9 hydrates. Sodium sulfite 5 hydrates, sodium sulfate 2 hydrates. So again we have here this logarithmic scale. So basically I can plot for salt hydrates exactly the same curves as I can plot for sorbates I've shown you before. Pressure as a function of time, of temperature. And as you can imagine, because these salts are hygroscopic, they have a lower vapor pressure than just the normal water vapor pressure at that temperature. Strongly adhere to the water molecules. Again, well, also you can see that we can see in these lines again a number of well-defined steps. Just as I've shown you before, this gravimetric graph, where the water came off in a number of well-defined steps with different equilibrium temperatures. So here we can see that given a certain vapor pressure, we have different equilibrium temperatures for the different transitions. Well, over here I plotted for all cases calcium chloride, but in this case absorbing water. So we have monohydrates, 2 hydrates, 4 hydrates, 6 hydrates, and the water line. For methanol, so we have the monomethanolate and here the methanol line. And ammonia, so calcium chloride monoammoniate, the ammoniate, 4 ammoniate, 8 ammoniate, and the ammonia line. So you can see it's all basically the same thing, but it depends on what sorbates you are having and what sorbent. The sorbate is the vapor, the sorbent is the material that absorbs the vapor.